Hello folks, this is a correction for the video you're about to watch. It is for Chapter 6, Lesson 5. It should say the title correctly on Google Drive, but when I announce this video at the beginning, and after a few seconds from now, it will say Chapter 6, Lesson 6, which is incorrect. It is Chapter 6, Lesson 5. Alright, sorry about that. Bye. Hello all, this recording is for Algebra 1, Chapter 6, Lesson 6, Linear Inequalities. Up until now, we've been talking about linear equations. Any linear equations are equations that, when graphed, create a line. Basically, there are many solutions that can make the equation a true statement, and they all lie along a line, which shows which points represent possible solutions. Now that we're talking about inequalities, inequalities possess far more solutions because there's a whole bunch of things that can still make them true without making them very, very close to exactly true. So, a linear inequality describes a region of the coordinate plane that has a boundary line. So that boundary line is like what a linear equation is, but then there's a shaded region of the coordinate plane that also contains possible solutions. So not only does the boundary line contain possible solutions, just like linear equations, but the shaded region also contains all the other possible solutions that could be for that linear inequality. So the solutions of linear inequality are all the coordinates that make that inequality true. And there's a lot of them. And again, that's why we're going to show shading. This is one of my favorite parts of math. Like I was saying, this is one of my favorite chapters because you get to do a lot of drawing and you get to do a lot of coloring. So what I recommend doing is, at least for your quizzes and tests, when I ask you to graph linear inequalities, that you either bring highlighters or colored pencils to show your solutions, and you might have a little fun coloring. All right, moving on. Like there's an example of a linear equation, right? And all of these possible red dots, or the dots, are possible solutions. So there's multiple solutions for linear equations, and the same holds true for linear inequalities, but linear inequalities have far more solutions. All right? Okay, so just like when we're graphing inequalities on a number line, when we did that, we had this solid dot, right? Well, a solid dot is when we're doing a number line. But when we're doing linear inequalities and we're having to graph on a coordinate plane, we're going to use a solid line to represent the less than or equal to and greater than or equal to symbols. When we're dealing with a number line and we have, just the less than or equal to, we use a open dot. When we're dealing with number line stuff, right? But now that we're dealing with coordinate planes, we're going to use a dashed line, which looks like a regular old number line, looks like a solid line, but you see there's openings right here. It's not a complete line. It's got some spaces. And just like when we're dealing with a number line, a solid line means that a solution could be exactly on that line. Whereas when we're dealing with a dashed line, the solution actually can't be exactly on that line. It can be very close to it, but a solution actually won't be on a dashed line when we have a dashed line. You could say it gets really close to this dashed line, but it can't exactly be on it. And then when we talk about shading, the moment you get to that dashed line and there's no shading on the other side, it means that up really close to that line where the shading are all possible solutions, but the moment you get to that dashed line, you get to an area of the coordinate plane where there is no where the solutions do not work for that particular linear inequality. Okay, so how do you actually graph a linear inequality? Well, you're going to graph the line and you're going to see it looks a lot like linear equations, just instead of an equal sign, it has an inequality. All right, use your knowledge about slope-intercept, standard, and point-slope form to help you graph. All right, remember slope-intercept means you're going to find the intercept, the y-intercept, and then you're going to use the slope to graph the line. Standard means you're going to graph the y-intercept and the x-intercept, and point-slope form means you're going to find the point and then use the slope to make your line. You need to remember this from the last chapter. That's chapter 5. If you need to go look at some videos, I highly recommend you do it because you need to be graphing these very reliably. All right? All right. So you're going to graph the line. You're going to make the boundary line correctly, either solid or dashed, and then you're going to test a point to determine shading because the shading is going to tell you all of the region where the possible solutions are. But again, because coordinate planes don't go on forever because our iPads and our pieces of paper only go so far. The shading actually goes on forever as well, okay? So just from looking at this, I'm going to technically skip to the second and ask you a quick question about the line. Is it going to be solid or dashed? Well, because it has the or equal sign, we're going to have a solid line. So when we get to that point, you already know we're going to have a solid line. Okay. Well, let's go ahead and graph this. This linear inequality is in the form slope-intercept, or y equals mx plus b. So we're going to go ahead and graph it using that knowledge. So there is my y-intercept, positive 3. And my slope is up 2 to the right one, up 2 to the right one, up 2 to the right one, up 2 to the right one. Excuse me. And you could also go down 2 to the left one. And guess what? It's still the same line. All right. I have some points that form a line. It must be a linear inequality. Go figure. So I'm going to connect the dots. There they go. And it is a solid line because, again, of the or equal sign, we have a solid line. Now we're ready to shade to tell me all of the possible solutions that work for this. Now, there is a side of the line that contains points that will not make this inequality true. But there is a side of the line, either the top part or the bottom part or the left or the right part, depending on kind of how your line is. You know, are we going to be looking at shading the left side or the right side? All right. So let's go ahead and pick a point. I like to use the point 0, 0. But you have to make sure that the point you do test is not on the boundary line. And as you can see there, there's my little warning. Never test points on the boundary line. It will give you a false positive because that boundary line, well, unless it's a less than or greater than, as opposed to the or equal to. Or equal to, any point on that line will work. It will work because it is a possible solution. It can include the points on that line. But obviously, if you use the less than or greater than, none of the points on that line technically work. But all of the points either to the left or the right do work. And we have to figure out which points do work on the left side of the line or the right side of the line, regardless of what the symbol is, other than an equal sign, obviously. Less than or equal to, greater than or less than or equal to, blah, blah, blah. All of those inequalities. So let's go ahead and pick a line. A point. I prefer to use 0, 0 unless it's on the line. You don't have to use 0, 0, and I'll show you an example where I don't use 0, 0 next. But let's go ahead and use 0, 0. So that's my test point, 0, 0. It is not on my line, not on the boundary line. So I'm going to plug in 0 for y and 0 for x and do some math. I'm going to get 0 is greater than 3. This is a false statement. 0 is not greater than positive 3. If you get a false statement when testing a point, it means you do not shade the side of the line that contains the point you tested. All right? If you do get a true statement, then yes, you would shade the side of the line that had the point. But since this is a false statement, if the point gives you a false statement, shade the opposite side of the line than the point. So if this is 0, 0, then I'm going to shade, and it gave me a false statement, which it did, I'm going to shade the opposite side of the line. Now, vice versa, which this is really hard to read, so let me get rid of that. There we go. So vice versa, if the point gives a true statement, shade the side of the line containing that point. But again, since I got a false statement, I'm going to shade the opposite side of the line than the point is on. So if I had 0, 0 and it doesn't work, I have to shade the other side. And again, you could test another point on the other side to prove to yourself that you're going to get a true statement. But if you get a false statement, you really, obviously, unless you're shaky on your math, you need to shade the other side, and you can just trust that your math was correct. Okay, so all of the points in this purple range right here are all possible solutions to this linear inequality. all of the points work. If you picked a point in the purple range and plugged it back into the purple equation over here, y is greater than or equal to 2x plus 3, you're going to get a true statement, which means it's a possible solution. So there's a ton more solutions than just a linear inequality, than a linear equation. A linear equation would just be like these purple dots, or any point on this green line. But since we have an inequality, there are dozens more, the 100,000, blah, blah, blah. There's a lot of solutions for that if it was a linear equation anyway, but the linear inequality has far more solutions, and there's so many that the only possible way to show them all would be on a graph and then just saying, hey, all of those points over there, all of those points in that shaded region work. Okay, so let's move on. So again, all of those points work. Okay, so let's go ahead and look at this one. This one is going to have a dashed line, and I know that because of here, right? Dashed line. Okay, so this one is in standard form, so I'm going to get my x-intercept, which means making y 0, which means I'm going to get x is greater than 2, which is, for graphing purposes, is the equivalent of x equals 2. Actually, if I go back, so x equals 2, okay? And there's my red dot over there on x equals 2. Now I'm going to get the y-intercept, where I plug in 0 for x to figure out y, and I'm going to get y is greater than negative 1/2. Now when you're doing this math, guys, if you get a negative and you're multiplying or dividing both sides of the inequality by a negative, you have to remember to do flippage. It's very important. Just because we're handling a different concept doesn't mean flippage suddenly disappeared, okay? So there's the next point, 1.5. Right there, right there. Okay, you guys got it. Okay, and I'm going to connect the dots with a dashed line, right? And now I need to pick a point to test. Now last time I picked 0, 0, and I could pick 0, 0 again. I'm going to pick a different point this time. Let's go ahead and test the point 2, 2. Definitely not on my boundary line. It's not on that red line there, right? So I'm going to plug in 2 for x and 2 for y, because I'm using the point 2, 2, and I'm going to get 28 is greater than 12. Hey, that is a true statement, and if you remember back from the previous slide, if you get a true statement, you shade the side of the line of the point that gave you that true statement. Since 2, 2 gave me a true statement, I get to shade the side of the line that contains 2, 2. It's a true statement, shade side with point. Shaded. Beautiful, right? So all of the solutions in that purple range will give me possible solutions to this linear inequality. All right, but the thing is here, you see here, it's very hard to see, it's in yellow, it's the point 1 3/4, 1 3/4, point 1 3/4. This point actually doesn't work because it's right on the boundary line, and since I have a less than or greater than statement, none of the solutions actually on that dashed line work. All of the points right up until that dashed line, that boundary line, work, but not actually on the line. So if you plugged in 1 3/4, 1 for x and 3/4 in for y, you're going to get a false statement, which is again why you can't pick numbers on the boundary line when you're testing a point. Can't do that. Okay. But again, anything not on the boundary line is fair game for testing. So the point 3, 4 and 1 3/4 is a solution. All right, and you can test that out to prove me right or prove me wrong, but I believe I did my math correctly. Okay. Next up is a word problem. Suppose you plan to spend no more than $24 on meat for a cookout. Your local market has hamburger for 3 pounds and chicken wings for $2.40 per pound. Find 3 possible combinations of hamburger and chicken wings you can buy, and basically you want to stay on budget. You can't go over $24. Right? So first thing we're going to do is we're going to write an equation. Though before I even get there, why do I have my graph over here set with basically the equivalent of no negative numbers? Well, that's because I'm not going to spend negative money on chicken. I'm not going to owe the market chicken. I'm not going to owe the market hamburger. I'm going to buy it. So I'm in the positive range here. Okay? All right, so we're going to write an equation. 3 times the pounds of hamburger plus $2.4 times the pounds of chicken needs to be less than or equal to $24. I can spend exactly $24, but I shouldn't be spending more than $24. And I can spend less than $24. I can spend $0, but if I spend $0, I'm not buying any chicken and I'm not buying any hamburger. Which is not quite the point of the problem, but hey, completely possible. Maybe I'm going to do a vegan cookout and this problem's just bogus. You never know. Okay, so we wrote the equation, and since it's in standard form, we need to solve for the hamburger intercept. Now the hamburger intercept is how many pounds of hamburger I can buy without buying any pounds of chicken at all. So that would be 8 pounds of hamburger. I can buy up to 8 pounds of hamburger and still be in budget, but I might not have bought any chicken if I buy exactly 8 pounds, because $3 per pound, 8 pounds, that's $24. So I cannot spend I cannot buy more than 8 pounds of hamburger based on how much money I have to spend. Okay? All right. Chicken intercept. That would be if I bought no hamburger. So I can buy up to 10 pounds of chicken. That's basically if I bought only chicken and not any hamburger. So I can buy 10 pounds of chicken at $2.40 and still only spend $24 if I only bought chicken. All right, connected the dots. Now, why is it a solid line? Well, it's a solid line because I can spend up to exactly $24, and the line represents how much of chicken and hamburger I can spend and spend exactly $24. All right, but what if I'm only feeding like 5-10 people and I don't need $24 worth of meat? Yes, I had $24 in my budget, but do I have to spend all of my budget, my meat budget? No, maybe I only end up spending $12. You never know. But again, I need to take that into possibility. So that's basically what we need to think about the shading. Which side of the line would be shaded? Now, basically, the line represents how much money I've spent depending on how much hamburger and or chicken I buy. So if the line represents exactly $24, the thing on the left side of the line, and when I mean left, I mean that side of the line, is spending less than $24, whereas this side of the line is spending more than $24. Because also, if you think about it, where is 0, 0 on this line? 0, 0 is right here. 0, 0 is if I spent $0. $0. No money spent at all. I didn't buy any chicken. I didn't buy any hamburger. I still have the $24 in my pocket. Am I still in budget if I haven't spent any of my money? Well, yes, you are. So you're fine. So we can test this point, and it will help you think about the shading. So I'm going to test the point 0, 0. If I didn't buy any chicken and I haven't bought any hamburger, am I still under budget? Well, yes, you are, because 0 is less than or equal to 24. So it's a true statement. So I'm going to shade that region. Now, the very last question they ask is 3 possible combinations of hamburger and chicken wings and staying within budget. Well, here's one. 5-1. Where I've bought 5 pounds of hamburger, 1 pound of chicken, and I am still under budget. Okay? That is great. I'm still in the shaded region. I could also buy 3 pounds of hamburger and 6 pounds of chicken and spend exactly $24 because the point is on the line. And finally, I could buy 1 pound of hamburger and 7 pounds of chicken and still be within budget. Okay, guys, I'm done. Bye. Hope you had a good Thanksgiving because I recorded this right after Thanksgiving. Bye.